The previous class that we had, it was to look on the other processes, that is the first three. And I said we're going to talk about the last two processes that we have as long we are dealing with a gas. That is, we have got what we refer to as the polytropic. It's another process that is important. All right, we've got the polytropic process, which says that this time we are going to have the law PV to the exponent of n, which is equal to C. This process is, or just mostly it is just working hand in hand with the adiabatic process. Under an adiabatic process, this is when you are dealing with what theoretical values. Polytropic, you are working with what practical values. All right. So it follows that, okay, let us just mention this at once, because I will be saying, I'll mention this and mention that. Let us just do this at once so that we see how we are able to attempt this. Okay, I need this one. Okay, sorry for that, guys. Very sorry for that. I just need to see if we can be able to win here. Let me just separate a little bit. All right, why is this line so ugly like this? I just need something like this. All right, so like I was saying, I'm just going to separate these two at once so that we just check what is the difference as you are revising as an individual. You know, all right, this is what I have for a polytropic process, and this is what I have for an adiabatic process. So under an adiabatic process, we are going to see that this time the law is given by PV to the exponent of gamma. You're going to use gamma in your calculations. All right, so this is it. We are going to have gamma. And it follows that, remember from the concept that we talked about, the heating of our gases, we said heat can be added or rejected. But under an adiabatic, no matter what, when heat is expanded or compressed adiabatically, there is no heat that is to be received. All right, so here there is no heat received, or there is no heat rejected. That is the condition that is going to differ between these two. There is no heat that is rejected or received. So that automatically tells us that Q must be equal to 0. Remember, Q for the heat rejected or heat received. All right, so this is the major difference that you're going to have, besides the issue of the gamma and the index of compression or index of what? Of expansion. Remember, I talked about this expansion concept and compression. Compression, as you are going up, so you're going to have PV to the exponent of gamma is equal to C. When it is an expansion, you're going down. PV to the exponent of gamma is also equal to C. Those are not going to change. So you just want to check the most important part, like how questions are going to be given, the formulas that you need also when working with each process. So one here, this part of our P1 V1 over T1 is not going to change, which is equal to P2 V2. You're going to be able to also apply this. You can use this to find any of this. And also remember, our PV is equal to MRT. Talked about this formula. It's not going to change also. This time, we are going to have under polytropic, we are going to have this one. Very important. Now, PV, but to the exponent of n. It must be to the exponent of n is equal to P2 V2 to the exponent of n. So this can be manipulated. Mostly they want you to calculate V2 or V1. We're going to see that manipulation later on. Then also there is this which connects the temperature, pressure, and volume. P2 over P1 to the exponent of n minus 1 over n is equal to V1 over V2 to the exponent of n minus 1. Need this. And also remembering that R is equal to the difference. I talked about that before, Cp and Cv. And this time, the change in internal energy also. All right, the change in internal energy, you shall also need this, the change in internal energy. Remember, we talked about this, Cv. This is the specific heat capacity to constant volume, Cp to constant pressure, times the change in the temperature, which is T2 minus T1. Okay, then also you are supposed to know the work done here, which is the work done. That is equivalent to, you can use the formula P1 V1 minus P2 of V2, everything over n minus 1. So this same formula, remember I said this P1 V1, P2 V2, MRT. So this can be given as MR into T1, which affects V1, minus T2, which affects the second part. Everything over n minus 1. In kilojoules, you can find your work done. We talked about these other units, guys. All these kilojoules are there, kilojoules per what? Per kilogram Kelvin. Then remembering that Q, the heat to be added or to be rejected, is the sum of the work done and the change in internal energy. So thus we can find whatever that we want from these formulas that we have there. With anything that we talked about before, we can find whatever that we want. So it is the same thing that we have under the adiabatic, but only that here we mention that the major thing that Q is equal to 0. But the concept that P1, V1 is not going to change. P1, V1 over T1 is equal to P2, V2 over T2. This is not going to change. And also, considering the PV is equal to MRT, PV is equal to MRT is not going to change. And the major important part that we need to talk about is the application of the gamma. This one, that gamma is equal to Cp over Cv. And remember that R is equal to the difference Cp minus Cv. So mostly they want you to use this to find whatever that they're asking there. So you are supposed to be able to manipulate that. Then this formula or this formula can be used, but in terms of gamma. So we can use this as P1 V1 to the exponent of gamma is equal to P2 V2 to the exponent of gamma, like that, which is the same thing also for this one. We can take it the same way. Maybe I'm given this and I want to apply it. I can still use it, still applicable, but all you just need to do is to have it in terms of what? In terms of gamma. So this is going to be gamma minus 1 over gamma in this case. All right, which is equivalent to what? V1 over V2. So this is V1 over V2, everything to the exponent of gamma minus 1. All right, this is gamma like this, gamma like this. These are just Greek alphabets that we're talking about, all right? These are Greek alphabets. This is what you need there, okay? So this is gamma minus 1, minus 1. So also, considering the change in internal energy, the work done, everything can be calculated. So also the change in internal energy, that is going to be mCv times the change in temperature, T2 minus T1. So this is going to be T2 minus T1. All right, then we talk of the work done. That will be the work done is equivalent to, we're going to have this as P1, V1, just like this part, P2, V2, but over what? Instead of N, we are going to use what? Gamma minus 1. So even on this side, it is the same MRT, the same thing that we had there. So it's going to be MRT1 minus T2. So that will be T1 minus T2 over what? That will be just gamma minus 1. That is the only difference that we have. And remember that we said here, this one is the only thing that is different. Our Q is equal to 0 under an adiabatic. So if Q is equal to 0, and before we said Q is the sum of these two, work done and internal energy. Remember, Q is equal to work done plus the change in internal energy, but we are saying Q is equal to what? To 0. It means I can write the work done in terms of internal energy. That means, therefore, the work done is simply negative the change in internal energy. All right, these units in what? In kilojoules and kilojoules, all right? Or we are simply saying the change in internal energy is equal to the negative of the work done. It's just one and the same thing. Once I have one, I can find another one by multiplying by a negative. That's what I'm simply saying. With these formulas that I have listed here, you are going to answer any question under a polytropic process or under an adiabatic process. You are going to answer any question. Any question. All we need is to use our formulas properly. So just because of this board that I'm using, guys, it's so complicated, I'm just going to move on to another page so that we'll be able to see our questions and we just try to apply those formulas. I think you have seen them. So just going to be able to recall and see. Example number 1, we are given a gas is compressed according to the law PV to the exponent of N is equal to C. So that's, we're talking about what there? A polytropic. Where N is equal to what? Where N is equal to 2. So take note, this is being compressed. Where N is equal to 1,2 from a pressure P1, which is 103,4 kilopascal, and volume V1, which is 0.0142 cubic meters to this pressure P2 of 413,6 kilopascal. At these conditions, find or calculate the final volume in cubic meters, which is V2. We do not know. The moment that we are given this N, it means this is no longer applicable for us to just say, okay, I'm used to this. PV is equal to P1, V1 like this. It's not going to work. This one is no longer applicable. We have to include N. So how do we write the same formula that we used to have before? We are going to write as P1, V1 to the exponent of N this time, which is equal to P2, V2 to the exponent of N. We are no longer using P1, V1 is equal to P2, V2 as we had from our previous class. So make sure that you watch that class so that you'll be able to understand, because this is a continuation. Just an introduction about the polytropic, but an intro, a continuation, I mean. So we need V2. We can make this V2 the subject. How? We can divide by P2. By P2, I want you to pay attention here. This will be V2 to the exponent of N, which is equal to this part. So I'm just going to start by this, V1 to the exponent of N times, just separate the pressures aside, P1 over P2 like this. It's the same. thing like we've got P1 over P2 times what? V1 to the exponent of n. So you can just start with V1. So if, remember from our mathematics, I want you to get this. How do you remove this exponent? X to the exponent of 3 from our mathematics, if this is equal to 27, how were you removing to the exponent of 3? You multiply by the reciprocal of this 3, which is 1 over 3. So by raising to the exponent of 1 over 3, you are left with x. So it is the same thing. I've got n. What is the reciprocal of n? It's 1 over n. So if I multiply by 1 over n, if I affect by 1 over n here, I'm removing this. That means I'm left with V2, which is equal to what? On this other hand, this is going to affect this part. So that means we're going to have V1 to the exponent of n to the exponent of 1 over n like that. P1 over P2 to the exponent of 1 over n also. This exponent affects this. It also affects here. But here there's a law, an exponent we multiply. So this will cancel. You're left with V1 to the exponent of 1. So this is n over 1 times 1 over n. This one is same as over 1. So n and n, they can cancel numerator to the what? To the denominator concept. So that means there, I'm just going to be left with V1 times, here there's nothing that I'm going to do, just going to remain as it is. So it's just going to be P1 over P2 to the exponent of 1 over n. So there we are now back to our mathematics there. This is your mathematics there. By substituting this, I can find V2 because I've got everything there. So V2 is equal to V1. Remember V1, 0.0142. So you're just substituting there, 0.0142 into P1. Remember our P1 was 103.4 and our P2 was 413.6 to the exponent of 1 over n, which is our index. There is 1.2. So that was the idea. Just substitute your values, you're done. So our V2 was going to give us, if we simplify properly, that was going to give us 0.00. Since you're going to need this, it's just rare to just complicated for us to leave this for. So let's just put it as 3 digits there after the comma, because we are going to need this volume. So that's our V2. All right. So with this V2, we can be able to calculate whatever that you want. Depending with, we need this V2. All right. So let us just write our V2 here. We got this one. Remember our V2, that's 0.00447 cubic meters. Okay, so that's how we play around these questions. Just have to be careful there. Then the work done in kilojoules, the work done under what? A polytropic. How do you calculate the work done? Under a polytropic. Remember, under a polytropic, we say that the work done is P1 V1 minus P2 V2 over n minus 1, which is the same as MR into T1 minus T2 like this over n minus 1. I do not have the mass. I do not even have the gas constant. So this formula cannot work for now. We can use this because we've got everything. The P1 is there. 103.4 times V1, 0.0142 minus, we calculated, P2, we already have this 413.6, but we calculated this V2, which is 0.00447. So that's your calculated value that you're putting there over n minus 1. What is our n? 1.2 minus 1. So this will give us the work done. Just like that. So that was going to give us a negative. Remember, it's under a compression there. That's we're going to have a negative minus 1.903 kilojoules. It is being compressed. Just like that. So they test you like this. They want you to understand the idea of what the process that you're dealing with. All right, another question that you're given, which is, it was actually the same question as the example 2, just where they just left it like that. But it was just the same as the example 2, so there was not worth it doing it. Anyways, example 3, we are given a mass of that is 2.2 of a gas is compressed polytropically. So under a polytropic, remember the idea there. PV to the exponent of n is equal to C. So we are given the mass in this case. Let us just take our information. The mass, that is 2.268 kilograms. Yes, you can have your diagrams for compression, but what you just need there is know that it's what? Being compressed. So the work done would be a negative if we calculate it. So it was compressed from this pressure and a volume of. So that is initially our pressure was 103.4 kilopascal and a volume which is 2.125. 125 cubic meters. To this. That is the pressure, the second pressure. So P2 was 3,120 kilopascal and a volume of V2 0.125 cubic meters. Given R in this case for air as 0.288 kilograms per kilojoules per kilogram Kelvin, and also CV, the specific heat capacity at constant volume, also given 0.67 kilojoules per kilogram Kelvin. We are supposed to calculate the index of compression N. Where? From where? How can we determine N? Okay. From the pressure volume that we have, remember we connected this previously and said P1 V1 to the exponent of N is equal to P2 V2 to the exponent of N. I've got P1 P V1 P2 V2. I have this from this information that we have there. So let me just make N the subject. There's an N there. Let me just make N the subject. So how can we make N the subject? All right, depending with how you want to work it out. Depending with how you want to work it out. As for me, I was just going to divide this by V2 to the exponent of N to the exponent of N, like so that this cancels. So I'm left with P1, this. So to remove this P1, I'm just going to divide by P1 so that this will cancel. And I've got V1 over V2. Remember, when you're having the same exponent like this, I can just have it as to the exponent of N, which is equal to P2 over P1. So I'm just going to make N the subject. Remember, from our N3, we had these types of questions where you make this the subject, introduce logarithms, or you introduce ln. But the moment that you introduce a log, here you drop the exponent. So that will be N, the logarithm of V1 over V2 is equal to the logarithm of the pressure in this case. So this other side here, we are dealing with the pressure. So it's the log of P2 over P1. So how can I find N? I just have to divide by that logarithm. All right, that's your mathematics N3 there. So if I divide by this log, it means N is equal to the logarithm of P2 over P1. Everything over the logarithm of V1 over V2. So I've just made N the subject. So I can just substitute everything. P2, 3 this over P1, I'm just substituting there. Remember, P2, 3,102. So N is going to be the logarithm of 3,102 for P2 over P1. Remember, it was 103.4. everything over the logarithm for the volume. So this will be the logarithm of V1 over V2. Remember our V1 from our volumes, just going to take as they are V1 and this V2. So our V1 there, 2,125. All right, so that will be 2,125. Everything over V2, which is 0,125. This. So that was going to give us N. And that was going to be 1,2002, something like that. So this is just approximating to 1,2. So that will be the best to work it like this. Just an application of the change of subject to transpose your N3 mathematics there. So that's N 1,2. That's what you needed there. So you never know, we might need to use this N. Let us just keep it aside. All right, so that is how they play around with you guys. They also want you to manipulate your formulas, work them out to determine whatever that you be given. All right, then the other part of the question was now to calculate A, the original volume, then B, the final volume, so the original and final temperatures in Kelvin. So we need the temperatures T1 and T2. So I think the PV can work there. PV has got MRT, we've got, yes, everything is there. So you can just use our PV there. PV is equal to MRT. So if this is 1, 1, this is going to be 1. So to find T1, just going to divide by MR both sides, MR both sides. So you remain with T1. So T1 is equal to P1, V1 over MR. So that's it. Pressure. The pressure at 103,4 times V1, 2,125. So that's it. Then everything over what? That's M, the mass. Remember, mass is 2.286, 2.268. So you have to multiply by the mass there. All right, and our mass was 2,268 times R there, which was 0.288. Okay, so that's gonna get T1. 336,391 Kelvin. That was what you're supposed to get there. So with the same calculations, I think we can do the same thing. PV, R there. So you're gonna do the same thing on the other side to calculate T2. So it means our T2, just gonna substitute here. Let us just put exactly how it was supposed to be from this formula. P it's gonna be P2 V2 over MR. So that's your T2. P2 already, we have it. 3,102 times V2, also 0,125. Everything over what? M, the mass, 2,268 times R there, which is 0.288. So that was going to give us T2. And with our calculations properly given, this was going to give us something like 593,631 Kelvin. All right, so these were the temperatures there needed. So just for the sake of our space, let us just save it here. So remember, we just calculated our T1 and T2. 336.391, which was our T1, and our T2, when we calculated, it was 593,631 Kelvin. So maybe you're going to need these values. Calculate the work done in kilojoule, the work done. Under a polytropic, how do we calculate the work done? Two formulas to be considered. Like I said before, P1 V1 is equal to P2 V2 over N minus 1, which is equal to MR into T1 minus T2. So I just hope I indicated that formula properly. If we are to check here for the work done under a polytropic, we're going to have this as T1 minus T2 this time. So that is what we have there. So meaning to say I can use any because I put the mass. There I can use any. I just want you to take any one that you want. So as for me, just gonna work with the first one. I'm just gonna work with the first one. So like I said, you're gonna choose what you want. So I'm gonna use this. P1, I have it 103,4 times V1, 2,125. All right, everything over what? N minus 1. Sorry for that. We have supposed. Where am I putting the equal to? There's a minus there. This is minus P2, 3,102 times V2, that is 0,125. Everything over what? N minus 1. Where our N, remember our N was 1,2. All right. Here, 1,2, we calculated that, 1,2 there. So that's it. We are going to have work done, and this gives us the work done in kilojoules. And it is like this. So meaning to say, in your calculation, you're supposed to be also very, very familiar with your units. With the units there, you're supposed to be very, very familiar. That was going to give us negative 840,125 kilojoules. Remember, I mentioned about the negative. It is being what? Compressed. That is why we see this, like the way that is happening there. Then the other part, they want us to calculate the change in internal energy. So the change in internal energy can be calculated. All right, remember that the change in internal energy is given by MCV T2 minus T1. Everything is there. So the change in internal energy, the mass, which is 2,268 times CV, constant volume. Our CV is 0,67 times the change in temperature, which is T2 minus T1. So that means we got have 593,631 minus T1 at the inlet. We had 336,331, 336,391. Okay, so that's it. We're going to have the change in internal energy, and that was going to give us 390,892 kilojoules. Just like that. So this part now is the most important. Like I said, we have to consider this. They are now saying calculate the heat received or rejected in kilojoules. So for us to have the heat, remember what I said under a polytropic, that in order for you to obtain the heat, you're going to need the relationship between the work done and the change in internal energy. So we calculated both. Everything is there. The work done, we got it before. It was a negative because the compression. So we've got negative 840,125. Plus the change in internal energy, which is 390,892. But it was a positive, this one. Okay, so this one, it was a positive. But if you get here our Q at the end, it was going to be negative 449,238 kilojoules. Like I said, the negative on Q means that the heat is being rejected. Not added, but rejected. So that was the case. That was just the case. Done. So this is how they just ask you typical person, they just want to play around to see, do you understand this? Even the same thing about an adiabatic process. It is the same that as we talked about there, that this, now we are using PV to the exponent of gamma, which is equal to when it is an adiabatic. So they are saying we are given a mass, in this case, of 0.454 kilograms of a gas, which is being compressed, right? So it's being compressed there from, and P1, 103 kilopascal, and T1, the temperature 15, plus 273, which is 288 Kelvin. So we are given the gamma there, which is gamma is given as 1,4. Remember the relationship between gamma that we had before. All right, I had a formula for this, CP over CV. Yes, that's it. Guys, now I'm tired, I can see. All right, and also R, which is equal to CP minus CV. Yes, this one. All right, then there we also have R, which is 0.288. Okay, so that was it. Calculate A, the original and the final volumes in cubic meters. We need the volumes there. The original, which is V1. All right. So at point 1, how can I calculate V1? I've got the pressure, the temperature, the mass. I can use my PV there. PV is equal to MRT, like that. So that means V1 is going to be MRT1. All right. What we want there is the volume. So you're going to divide by P1. So that's going to have V1. That's just a substitution there. 0.454 times R for air. That's 0.288 times T1 initially, which is 288. Everything over what? P1, 103. So this was going to give us the velocity, the volume, right? The volume there. That will be 0.366 in cubic meters. So you check if the same situation or scenario is happening on the second part. Are we having second part? There's nothing at all. There's nothing that we have. It's nothing. All right, seems like I left something there. The pressure to this pressure. So it's only the pressure that we have here. 1030 kilopascal. So we do not have the temperature. We do not have the volume at this. So it's going to be difficult for us to have that volume. And also they need the temperature at the end. So what are we going to have? What are we going to do? Remember, there's that formula that we connected before between the pressure and the volume. Since we want V2. All right, we say that P1 V1 to the exponent of n is equal to P2 V2 to the exponent of n. And I manipulated this to make V2 the subject, guys. I'm not going to talk about this anymore. I'm just going to make this the subject. So we said P2 will be, V2, will be given as V1 into P1 over P2 to the exponent of 1 over n. If you still remember that manipulation. So there was just, it was just a matter of substituting. So that's our V2 is going to be V1 that we calculated 0.366 times P. This will be P1 over P2. Pressure, we have them. P1, 103 over P2, 1030 to the exponent of 1 over n. And thus, okay, the process there has changed, guys. This is an adiabatic. So the exponent of what? Of gamma there. I hope someone was seeing this. Why are we using this? No, we're supposed to use what? Gamma there. All right. So this is our gamma, which is 1,4. So that's it. We were going to obtain our V2, which is 0.0707 cubic meters. So that is how we can play around this type of equation. Then now they want you to find or to calculate the work done in kilojoules. The work done. So to find the work done under an adiabatic process, remember we can do this to calculate the work done. Okay, did I not leave any question here? All right, I need to find out I left another question there. The final absolute. So it's either I can use this V2 that I calculated, this one. Sorry for that, guys. I had left this one. Just remember these values because I'm going to remove them. But remember the values that we calculated in case that we might need. So here they want us to calculate number two first. The final absolute temperature, which is T2. All right. Then now I have RP. And remember, I just calculated the volume. Right now it was 0.0707 cubic meters. So I can trace back. From our PV, it can work this time because the volumes are there corresponding at 0.2. P2 V2 is equal to MRT2. I want to find T2. So simply I can divide by what? By MR. All right, let us substitute. Everything is there. We calculated, or some are already there originally from our information. So our T2 was going to be equal to P2. That's the pressure there, 1030. Times V2, the one that we calculated. Everything over the mass. Times our R for air, which is 0.288. That's the idea. So you see, as long you know your formulas, you won't go wrong under this. It's just a matter of applying your formulas. So T2 was going to be 556,940 to 3 decimal places. It's just going to be 40. Okay. Then now they want you to calculate the work done in kilojoules, the work done. Remember that this is an adiabatic process, so the formulas are still not going to change. They are not going to change for work done. P1 V1 is equal to, minus P2 V2 over what? This term is going to become a minus 1. Which we can use the MR formula. Everything over gamma minus 1. I think we never did this. Let us just talk about that. Yes, we can use this. It's fine. But let's just talk about this one. Do we have the mass? Yes, we've got the mass, 0.5454. So we're just substituting there the values that you're given. Okay, sorry for that. Let's hope we're going to be able to finish, guys. That's 4 times this. So there you just have to substitute all your values. All right, if 87,911. Guys, as you can see, this has affected everything, this board. Sorry for that.